Hello everyone, welcome to the second lecture on reinforcement learning from the reinforcement learning submodule. This lecture we're going to be talking about Markov decision processes. Now, Markov decision processes are really just a formalism that help us to model the majority of reinforcement learning problems. So we're going to start off by just recapping on what Markov states were, but we're going to add a little bit of dynamics to the states, which is the probability of transitioning between the states, and that's called a Markov chain. And then we're going to add rewards into the equation, so we're going to sort of layer on a bit of functionality to a Markov chain to have what's called a Markov Reward Process. And then we're going to add a little bit more functionality onto the Markov Reward Process, where we're going to introduce actions, which is going to give us our Markov Decision Process. So Markov Decision Processes, we're just going to look at defining them today, really. But after the live coding lecture next week, we're going to introduce algorithms which actually help us to solve them. And today we're just going to be studying some very, very small and simple Markov decision process examples. However, the ideas you'll be learning in this lecture, you'll be able to extend and use more powerful techniques like deep neural networks to solve MDPs with sort of 10 to the power of 100 states. So in this lecture, we're just going to look at MDPs in their sort of low-level matrix forms, but later we're going to sort of say, well, actually we could approximate these functions by sort of deep neural networks to solve them for much larger states. So let's just have a quick recap on what the Markov property was, or what Markov states were, information states as we also called them. So here, if you remember, a Markov state was just one that completely sufficiently captures all future events. So you can throw away everything before it if your dynamics, if your environment can be expressed in terms of Markov states. For example, if you have a chessboard, just by looking at the chessboard, you actually know everything you need to know about the game to be able to behave optimally from there on. You don't need to know up to that point in time what moves your opponent played or what moves you played. Sufficiently by looking at the chessboard, you know how to behave optimally from there on. And if you remember, conversely, we talked about that example where there were cars in a race, and imagine there were two cars close to the finishing line. If you just had their two positions, that wouldn't be sufficient to tell you who is going to win the race, because, for example, one of the cars might have broken down, the other car might be accelerating rapidly. You really need that extra information. You need the velocity, the friction, the weather conditions, the car weights. You need all of that to be in the states themselves to make them Markov, to be able to make them sufficient to tell you who's actually going to win the race. And then we had this equation down here, or this notation, where we said the distribution over the actions and events for the entire future is conditional only on the Markov states, which is the same as if it were conditional on the whole of history. So you can actually throw away all of history if your states are Markov. So what is a Markov chain? Well, simply, a Markov chain is where you've got your states, like being in the pub, being in your room, being in the car. So you've got these kind of labels for your states, but you also have the dynamics. You have the probability of transitioning between the states. So you can express this as a state transition matrix, or this is how we would define it. We would say there's some probability of going from one state to the next state, this S prime. And that's just the probability of the next state is conditional on the previous state. So this is some probability of transitioning from state to some other state. And for all the states in our environment, we would represent these probabilities as a matrix where you would have, down here you would have like A, B, C, and the probability of transitioning to the states A, B, C here. So I could give a sort of very simple example just in my notes here. If I just push this down. Okay, I'm just going to switch that over. So a very simple example of a state transition matrix would be to say P equals, maybe we've got some state A, B, C. We could just say, for example, there's a 0.3% probability of the state A transitioning to itself. Then there's like a higher probability of transitioning to the next state B. Then there's 0 probability of transitioning to C. then B could be, for example, a 100% probability it always transitions to state C, and state C we could say has a quite low probability of transitioning to state A, quite a reasonable probability of transitioning to state B, and also quite a reasonable probability of transitioning to state C. So that's an example of a state transition matrix. Okay, just bring that back. So we've also already sort of briefly touched on what a Markov chain is, but a Markov chain, also called a Markov process, is simply the labels of your states, or a set of states, and also these transitional probabilities, this matrix here, if you like. So formally it's a finite set of states, where P is the state transition matrix, and we've already looked at that equation, the probability which captures the probability of transitioning between the states. So this is a really great example by David Silver, and it really sort of shows a nice concrete example of a Markov chain. So I'll just walk through this. Basically we have these states. We have the state of being in one of the classes, maybe on this course. So there's 3 classes you can attend, and if you go to all 3 classes, then you could hopefully pass, and then once you've passed with 100% probability, you can go to sleep and you're done. But also, if you're in class 1, you might find the content slightly boring, so you might decide to watch TV. There's an equal probability you could go to transition to class 2, but equally you could transition to watching TV. But when you're watching TV, maybe your favorite TV drama on Netflix, let's face it, there's a very high probability you're just going to keep watching TV. So you're going to be addicted to Netflix. And there's a very low probability that you're going to actually come out of that state, which transitions to itself, back into class 1 again. And when you're in class 1, hopefully this time you'll transition into class 2, and maybe now with a high probability you'll go to class 3. But now you're in class 3, you might be quite tired, so you might decide to go to the pub with some probability, 0.4. And when you're in the pub, who knows where you're going to end up. I mean, you could end up going back to class 3, but maybe you've had one too many drinks and you need to remember what you just studied, so you might go back to class 2. Or maybe you've really had too many drinks and you're going to have to go all the way back to class 1 because, let's face it, you've just forgotten everything. Then when you're in class 1, maybe now you transition back to class 2 again, but maybe now you've had enough, so you just go straight to sleep. So we can actually represent that whole process as a as a state transition matrix, all of those dynamics, where you can see the states captured here and here. And actually there's a nice demo, and I've just sort of plugged in something similar to that here, so you can have a look at how the agent interacts. Currently it's stuck in one of these self-transitioning states, and now it's here it is, it's playing an episode. And you can see how it transitions around the states with some probability. Here it's stuck in this self-transitioning state G again. Maybe that's watching TV and so on. I've just removed the terminating state here, otherwise it would get stuck and be a bit boring. So once you finish and you reach the terminal state, we would say you've completed the episode and you're done. So formally, an episode is a varying length sample of a Markov chain. So it's where you go through, maybe we start at class 1 always, maybe that's our initial state, and then a short episode might be, or an optimal episode might be to transition to class 2, then on into class 3, then pass, and then you're done, you can go to sleep. So that's quite a short episode. An even shorter one might be to go from class 1 to class 2 and then straight away to sleeping. But similarly, we could have a much longer episode, which is where we just sample this Markov chain, and we start in class 1, then we start watching Netflix on TV, we keep watching another episode and then another episode, then we go back to class 1, then we go to class 2, then we go to class 3, then we go to the pub again, then we go back to class 2, and then maybe you sleep. So these episodes can actually be very, very long, but there's because of the Markov property, you're always going to terminate eventually. So it will always be you will always reach this terminating condition. Okay, sorry. Sorry, excuse me. So that's a Markov chain, and the Markov reward process basically introduced the notation of rewards into this Markov chain. So it's a Markov chain, but we additionally have what's called a reward function. And the rewards are, it's just some function which gets reward. For example, it could be like extracting some pixels from like a game's display. It could be like extracting gold from the game states. But if we recap from like what we touched on last week, we said that at each time step t there was just this scalar signal which was called the reward. Okay, so we had those examples where we talked about time-based goals where you might like lose reward every time step. We might have like the forward motion of a robot, or in chess we might have just reward only when we win and we get checkmate. Or you might have like multiple goals, and if you've got multiple goals you need to sort of balance your rewards out carefully for your decisions. And then do you remember we talked about briefly how designing rewards was actually a challenge, and we talked about like Demeter's touch in Greek mythology where he has this idea but it doesn't turn out well. So formally the R is a reward function where the reward at a given state is the expected value of the reward conditional on the state. Okay. And there's also this discount rate here, this gamma, which helps. We'll come on to it a bit later, but it basically helps us to penalize rewards as we go on into the future. So let's just add these rewards into our Markov chain. So we've now got our Markov reward process example. And here the red values are to be basically read upon entering the state. I'll receive a reward of -2 from the environment at RT plus 1. This idea of, if we go back to the definition, this sort of RT plus 1 here is actually Sutton and Bartow notation, and it's kind of done on purpose to denote the boundary of changeover where the agent receives the reward from the environment. And then if you remember, we talked about it was the environment that gives the reward, not necessarily the agent. So we would say upon entering class 1, the environment gives us the reward -2. Upon entering class 2, we get given another reward of -2 back from the environment. But basically it's kind of like the immediate reward. So a lot of people are confused by this idea that RT plus 1 is considered the immediate reward, and some literature actually does go as far to define it otherwise. But again, it's just Sutton and Bartow notation, and it does make sense, and it really helps drill in the idea that in these formalisms we're talking about the environment giving us the reward back to the agent. Okay, so in this case here, we don't really want to have this cycle where we keep getting positive reward here, so we lose reward by watching TV, even though it might be sort of enjoyable in the short term. But every time we go to the class, it's pretty tedious usually, so we lose some reward. Going to the pub's quite good though, but then you've still got to go back to class at the end of the day. And then once you've passed, then you get a big burst of reward, and you can sleep. And once you've terminated, that's it. That's the end. So the return is, well, the return, really the future reward is called the return, the future reward, and it's parameterized by this discounting factor, or this diminishing factor, gamma. And gamma is typically a scalar less than 1, where we have gamma to the power of k for the k future time step. And basically we may wish to penalize rewards far into the future. So the return is just sort of all of the rewards going into the future. So if you play an episode of a Markov reward process, at every state we're going to basically want to sum up all of the rewards going into the future. And but when we're talking about the return, there's lots of reasons why you might not want to just like have all of the future rewards counted equally. that would be quite sort of long-sighted behavior. So we might want to penalize it for various reasons. So if we were to set gamma to 0, then you can see this is just going to zero out this term, which is going to zero out this term. And so we're only going to be counting the immediate reward if gamma is 0. So we're going to have this kind of short-sighted, not very intellectual agent behavior. Whereas if we were to set gamma to 1, then gamma to the power of k, or 1 to the power of k is equal to 1. So all of the future rewards are going to be counted with equal weights. So that's this kind of far-sighted evaluation. So you can kind of think of it like if you just like set gamma to 0, it's a bit like being a kind of heroin addict. You're going to just get your immediate burst of reward and then detrimental to all of the negative consequences that will have into the future of your life as you get addicted to heroin and just keep injecting yourself and everything fails, your career fails and so on. Whereas if you've got that like long-sighted reward where you set gamma to 1, all of the future rewards have equal probability, which means if you have a very long episode, so maybe this is representing your entire life, then it means you're going to sacrifice yourself crazily in the now to maximize your long-term rewards. So maybe you'll just like study, never meet anyone, but you're going to have a very successful career or so on. So you can kind of think of it like making your agent have various political or religious incentives. However, the uncertainty does increase in the future. So so we can't really model the future. So there are actually quite good reasons to not have gamma so high as 1, but to lower it a little bit. And actually mathematically it's convenient, so you will get better performance because you'll have shorter episodes if you don't need to go so far ahead. Another nice thing about this discounting factor is it helps us handle infinite loops in the state transition graphs. So if there are like infinite many states in the Markov chain, then the return will always be finite if gamma is less than 1. And also there's like a biological motivation behind this discounting factor, which is that if you actually look at animal and human psychology, we actually have preferences ourselves to immediate rewards. We tend to have our own slightly lower gamma internally, which helps us to chase after short-term goals. We're not very good at chasing after very long-term goals and having master plans like Elon Musk does. So that brings us on to the state value function, or the value function. And this is a really central idea in reinforcement learning. So the value function in a Markov reward process is the long-term value of a state. So every state, you can say, has this value function, which is defined as the expected value of the return conditional on some state. So every state has this expected value of the returns. And this is really calculated by sampling lots of episodes and averaging. So if we consider this puppy here, it's really enjoying the reward now. And it's in quite a good state here. But maybe this state to be in, it's not like as good a state to be in as the puppy might think, because in the future, this state might involve the owners having to discipline it. It might not get dinner even though it's just had a slight taste of the Thanksgiving meal or whatever it is. So the expected long-term value of this state for the puppy isn't actually that particularly low, because on average the owners are going to discipline this puppy and be angry at it. So the value function is really a way of saying what is the value of being in this state on expectation from where I might end up by going from this state. So what is the long-term value of me being here? Okay. So let's try to look at some examples. So this is where we try to look at the value function for S, and we're just going to sort of say what is the value of being in the state of class 1. So if we say gamma is equal to a half, so it's kind of not necessarily immediate reward, not necessarily fully long, far-sighted reward, then if we take our definition of gamma, of the return, the discounted return GT, and we plug in half. Basically, now what we do is we have to sample lots of episodes, and we can then begin to compute the value of the return here. So, for example, if we've got, here's one episode where we go class 1, class 2, class 3, pass and sleep. Then we take the reward of -2 for being in class 1, that's over here. And then we add well, in this case we're negating because we have a negative reward, the reward of class 2 as it's discounted by gamma. And then we keep doing that, so then we add on the reward of being in class 3, discounted by gamma, which is now a quarter, and then we add on an eighth of, because we're now gamma to the power of, I can't remember what it is, but an eighth now of the reward of being in class 10. And then we're in our final episode, which is just 0. So if we add up all of those values, if you plug this in, you'll get some value of negative 2.25 for being in this state for this episode. And as you just randomly sample episodes from class 1, you're going to get different returns as you sample through the episode. So here's another episode from class 1, here's another episode from class 1. So you get like lots and lots of these returns out of it. And then the value function is just the, if you remember the definition, it's the expectation of those. So it's just really averaging all of these returns, and you will end up with some value for this. So I think I've got a demo of this. So you can access these demos from Duo. You can just click like the collab link next to the corresponding lecture materials. So I'm just going to here define our states, which is just straight from this example. And okay, so let's just run that. And this is just checking that they all sum to 1. And then we're going to have this function here which samples some episodes. There we are, we have some nice samples. And then here we're going to just basically, so this is just sampling this Markov process here, just as we've seen. And we can actually just type sample episode as many times as we like. Let's just do another just so you can see it. So here's a sample of an episode. And you can just run this as many times you like. Under the hood it's using like numpy.random choice. So it's just working out when it should transition based on the probabilities as defined by this state transition matrix. And you can just sample this as many times as you like. Yeah, we've got a really long one now which just watches lots of TV. That's a huge amount of TV this guy watches. Oh, there's another long one. Let's see if we can get a short one. And there's a short one. That looks like an optimal one, actually. So now, how do we compute the value of being in class 1? Well, really, we just need to keep averaging it. So it's actually a Monte Carlo method. So let's just run through what's happening here. We're sampling an episode, and we're computing the reward at that episode. And then we're going to just go through the entire episode and compute the return as per the equation. Okay, and this is quite a long episode. Let's see if we can find a short one. So this tells us the return for this episode here. Okay, so how do we solve the value function? Well, we're just going to solve it iteratively. So we're just going to do lots and lots of samples, and then we're going, like in the table here, we're just going to do maybe hundreds of samples or thousands of samples, and we're just going to average it all together. So here we have, we're going to go through lots and lots of episodes, and then for each episode we're going to calculate the return, the discounted return, and then we're just going to divide or average by the number of episodes. So let's do that. Here we go, these are all different episodes. And this is actually for all of the states as well. So this is the value, I believe, for one of the first states. Okay, so this tells us the value for all of the different states just by this iterative averaging process. And you can see how at the beginning it sort of starts off not very good, and it starts to converge on the true value function over lots and lots and lots of trials of different episodes and lots of averaging. Okay, so if we put that all together, we can say that we can actually compute the value of being in every state. So we can see just by eyeballing these values the best state to be in is this pass state where we've got most value. Then it's quite good to be in class 2. We've got like 1.12. Then it's not quite so good to be in the pub. And it's not that great to be in class 2, negative, and it's really bad to be in class 1, and so on. And then at sleeping we have 0 value. Okay, and now this brings us on to another really central idea of reinforcement learning, which is really where a lot of the advances in this field have come from, which is the Bellman equations. So we want to know how good it is to be in a particular state. We want to know the value of the states, as we saw. And the Bellman equation really just follows a series of identities that rearranges that value function definition into a more localized and efficient form. So if we just kind of read the equation as we go down, we say that the value function is the expected return given that we start in some particular state. Okay, that's just a definition of the value function as we've already seen it. So we could unroll the definition of the return. So we already defined what the discounted return was, so we can just plug that in. So we could say it's the sum of the rewards going into the future, discounted by that gamma rate, okay, and conditional mean the state. So we've already seen that, we've just substituted that in. And then we can actually factorize this just by looking at it. So we could actually pull gamma out, okay, and we could pull it outside and factorize it there. And now you can see we have the definition of the return again. So you can see that from this we've actually got inside here another sort of mini definition of the return. But instead now we're starting at the next time step of gt plus 1. So all of this part here is just the same thing as saying it's the return at the next time step. Okay, and that actually brings us on to the final part of the Bellman equation, but it's really just saying it's the immediate reward plus the discounted return at the next state, which is the same as saying it's the immediate reward plus the value function at the next state. So I don't know if you remember the maybe I can put this down from our previous lecture, the definition of the expectation. We said that the expectation of some random variable x is equal to summing equals 1 all along little x times the probability, little xi times the probability. So we can actually integrate with respect to this probability the next state. So the value of the transition, replacing that expectation here by summing all of the discrete kind of states, the probability times the value function at the next state. So so that leads us into this equivalence here, where we can just say that the value function is actually equal to the reward at this state plus this discounted idea where we sum all of the next states transitional probabilities. So it's summing all of the probabilities transitioning to the next state. So we've kind of broken down that idea of the return into this sort of immediate look ahead idea of the value function. So we still need the value function at the next state, but we've decomposed it, so we've now only we can compute it locally. So just to read what we wrote here, for a series of identities we can decompose the value function into the immediate reward and the discounted value of the next state. And actually this can actually all be expressed with matrices, which is actually a linear equation that can be solved. So it actually requires a matrix inversion. Let's just go back to here. So yes, you need to invert the matrix, but you can kind of read about that, and the matrix inversion complexity is about O(n) cubed. But there are quite more efficient ways to do that matrix inversion. You can read on Wikipedia about the kind of asymptotic complexity of the bounds. You can actually reduce it to ON to the 2.3, something around there, by the Coppersmith-Winograd algorithm. However, in practice, these have really high constant factors, those kind of like matrix inversion libraries. So it really is ON cubed out there, which and you would use like BLAS and Alpac, and they do like NumPy calls, and they're hand tuned to really outperform the theoretical Coppersmith-Winograd algorithm. So you really have that bound in there. So unfortunately it is quite slow, except for very, very small MDPs. But I'll just show you in the code here what it means to solve that linearly. So this basically shows it. If we plug this in directly, we can solve it using the library, which is, and I've shown the equivalence there, but this is just the solution output, which tells us the value function for all of the states. But that's just not something you can do with a very, very large state transition matrix. But it's nice to just see that it can be done. There's a nice closed form solution for it. So should we actually verify this? Let's verify this value function here. So it's quite cool because we can actually estimate the value of a state far into the future just by its local conditions. So here, if we look at class 3, the value function 1.12 according to the Bellman equation, we can see just by the definition it's the reward plus the discounted value of summing the state transitions to the next state. So that's just equal to, let's start here, the immediate reward, which is -2 of this state here, plus the discounting factor gamma, and we're just setting that as equal to 0.5, so that's here, times, and then we're going to start by saying it's 0.6 because we're summing over the transitions, the probabilities, so it's the probability of transitioning to the past state, so it's 0.6 probability times the value function at the next state, which is this 10v here, and then we're also going to sum. So we're going to add also the probability of transitioning to this state, which is 0.4. That's the probability, times the value of this state, which is 0.062. And if we evaluate all of that, we get the actual value function, which is 1.12, which we can confirm is true. Okay, sorry. So that helps us to verify very quickly that this is truly the value function just by the Bellman expectation equation here. Okay, so now we can actually move finally onto Markov decision processes. And we're basically going to be redoing, let's see, sorry, no, so in the discrete case, you can think of this as having like a separate transition probability matrix for each action that you take. So we're introducing this notion of actions. So we now have a finite set of actions, and it's really like saying for every action that you can take, you have this new transition probability matrix. Okay, so if we just go through here, now we have the probability for an action of transitioning between the states. So we say it's equivalent to the probability of transitioning to the next state, conditional on a state, but also conditional on an action. And the reward function, similarly, we have for actions. So the reward for an action, taking an action under a state, is equal to the expected immediate reward, the expected value of the reward, conditional on being in a state and taking an action. So we add actions to our MDP, and kind of redoing David Silver's example, we now have like new decisions that we can take at any point. So the actions in this case are represented by black dots, and they're kind of like the choices the agent can take. And there's no probabilities anymore here, there's just choices. Okay, so the agent in class 1 can choose the action now of studying, or they can choose the action of relaxing. And if the agent chooses to relax, they end up in this state watching TV. But if they choose to study, then they end up in the next class. Whereas when you're in class 3, the agent could choose, for example, the probability via its policy of going to the pub. And then we would say that here is the only place where there's like some stochasticity of the action. All of the other actions are basically like having probability 1. But who knows what happens at the pub? You may end up like drinking more and ending up in like one of the classes. So the environment dynamics basically determines which state you end up in. So with like a Markov decision process now, the agent has a lot more control over its actions. And to formalize this new control, we need to define like the distribution over the actions. That's what we're going to come on to. Okay? So this is really what a policy is. A policy is a distribution over the actions which determines how agents should behave in the environment. So the distributions over the actions or actions given the states. So in other words, if you're in some state S, then the agent can learn a distribution over which actions it should take. If it was in the class 1, you could map to some probability of relaxing and some probability of studying. And if it's a lazy agent, if the policy is to be lazy, then it would have a higher probability of relaxing. Whereas if it's a hard-working agent, then it's going to have a higher probability of studying. So under the hood, you can express that as a stochastic transition matrix, or it could be a function we learn, such as like a neural network or something. Okay, so just reading the definition here, a policy is a distribution over actions given a state. So it's this probability of the actions conditional on the state. So you may be asking yourself, like, why is there no reward in the definition? And the reason is we don't really care about any of the previously accumulated reward. We just wish to learn how to maximize our rewards going on into the future. So if you've got like lots of money, we only care about making more money. So to behave optimally, we only care about maximizing the reward from now onwards, which is captured in the future states due to the Markov property. That brings us on to the state value function. So the state value function is the same, it's the value function, but now it's for a given policy. And if you record a value function, it assesses how good it is to be in a given state, and it was computed by calculating the return of total future rewards. Well, now it's the same, but it depends on the policy. So again, if we're lazy, we're going to get less reward than if we study hard. Or suppose suppose we're the agent and we're in a state near this bright Angel Trail in Arizona. There's this really nice view up ahead. So this state has quite a good value, right? And an energetic policy would skews the distribution, if you like, to just keep walking upwards. Whereas a lazy policy distribution is skewed to go back home. And likely that policy is going to miss this S prime, where it's got this more beautiful view going into the future. So that's the state value function, but also we have equally an action value function. And the action value function is the long-term value of a state when choosing an action with a policy pi. So for example, for my state on the Arizona Trail, suppose I have two actions available. I could either keep walking, and you could reach that state of having a beautiful view, or I could choose like the next state to just like jump off and die. So you can see if I was to choose the action jump off the trail, even if I was like following the energetic policy, it would still have a very, very bad reward in the future because you'd be dead. All right, so the action value function basically says if I'm in this state and I take this action, what is my expected return going to be under that policy if I'm in that state and I've decided to take that action. All right, so it's a little bit more information, I suppose, to the value function. It also tells us the value function if we're taking a given action where we're going to end up, always under that policy. And similar to Markov reward processes, we have the state value function can be decomposed into the immediate reward and the discounted value of the next state. So we can apply our Bellman equations to this. So just reading the slide, we can basically say the value function is the expected return, and then we can go through all of those identities as we saw and break it down into the immediate reward plus the discounted value of the next state under that policy. And we could also, similarly as we saw, we could take that expectation and turn it into a summation just by the definition of the expectation. So we're summing over the actions for the policy of the action conditional on the state times the Q value here, which was the action value function. So we also need this definition of the action value function, which we have here. So the action value function is the expected value of the return conditional on the state and the action, which again we can similarly decompose. So we could like replace this action value function with a new definition. You end up with this like recursion, which means we can actually understand this whole thing in terms of itself, which is actually how we solve MDPs. So we could, for example, if we just look at this a bit more detailed, we have the expected value of the reward of the next state plus the discounted action value function of the next state and action conditional on a state and action, which similarly we can see is the same kind of idea happens. It's the immediate reward for that action in that state plus the discounted value summing over all of the next states of the transition probability times the value function of the next state. But basically you see this value function in here, they depend on themselves. So this depends on this value function definition, which itself has this Q function definition, which we could take this definition for. So there's this like recursion, there's this kind of idea of this recursion here. All right, so here's an example of applying that to David Silver's lecture, where we're going to compute the or verify that we can actually compute the value function for this Markov decision process. So we're going to just assume that we have some average policy where the policy is to just randomly choose actions. So sometimes the agent chooses to work really hard and other times it chooses to go to the pub. So every time it's got one of these little branches here where it could choose this one or this one, it's always just going to say 50% probability. So it's not lazy, it's not hardworking, it's just a bit random. Okay, so that's our policy. And what we want is under that policy, what is the value? How do we compute this 7.4 value here? And I'm just going to show it by verification. So the definition of the value function being in that state under that policy is as we just had in the previous slide. And what we tend to do is we reach this Q star and we just take the definition of Q star, which is here, and we substitute it. So we now have this larger value. And this is what we're going to use, this equation here. So actually applying this, what it tends to do is it's like a one-step look ahead. That's the best way to think of it. All right, so let's just start by this action here. So there's 50% chance under this policy pi of taking this action. So it's 0.5 probability. So this is the policy. So it's 0.5 probability, so 1/2 here, times the reward here plus, and there's nothing in the future for it to consider, so this all just zeroes out. So we just get 0.5 times 10 for this action here. Okay, but then we add the value of being in this state, of taking this action here, which is a little bit more complicated. So let's just work our way through this. So we have 0.5% probability under our policy of going to the pub. So it's 0.5 for our policy pi here, times, and now we're going to do our one-step look ahead. So this is all of this stuff here. So it's the immediate reward of being in the pub, which is simply 1. And then what we do is we add our discounting factor, and we've said that's 1 times, so we can just get rid of that 1 because it's 1 times something. And then we're going to be looking at the future states value functions and their times by their state transitional probabilities. So when we're in the pub, the next state is going to be class 1, so it's 0.2 times negative 1.3, the value of negative 1.3, plus 0.4 probability of going back to class 2, which has a value of 2.7, plus 0.4 times the value of going back to class 3, which is 7.4. And then when you add all of that together, so you've done this kind of one-step look-ahead process, you get the final value, which is 7.4. So that verifies how we can use the Bellman equation with that kind of one-step look-ahead, local bit of computation to compute the value function. And yeah, you can actually solve that for a given policy directly, again, achieved by averaging it. So you could end up with like a Markov Reward Process, which was solvable as a linear equation for that given policy. And it's all very well because it tells us like the expected behavior, but it doesn't really tell us how to behave optimally. All right. What we really care about is figuring out how to optimally play these games. So, for example, like Mo Farah winning the gold medal here, for him to get the best possible value, he must also have the best possible policy, which is like doing all his warm-up routines, his dieting, his pacing strategies. And if let's just read the definition of this, which is to say that the optimal state value function is the maximum value over all policies. So the optimal value function for being in a state is the maximum for all policies of the value function of being in that state. And V star here tells us the maximum amount of reward you could extract from the system. So similarly, Q star, or the optimal action value function, tells us the maximum amount of reward you can extract when you start in that state and you take that action A. So what's the best time Mo Farah could possibly get if he chose to eat a hamburger instead of his usual chicken and rice in the morning of the race? But then if he did everything optimally from there on, all his training and his warm-up routines and his pacing, if he did it all perfectly, what's the maximum time or the best time, I suppose the smallest time he could possibly get? And if you have Q star, you're done. The MDP is considered solved because it tells us everything we need to know to behave completely optimally from there on. It tells us which actions to take at which dates to always win. So we can kind of just eyeball this to see how it works. So like if we look at this example here of these optimal value functions, if you're in class 3 here, should you go to the pub or should you study? Well, 10 is the optimal value. That's where we get our reward. So the max of 10 and 1 is 10. So you should study. That's the best action you can take in class 3 is clearly to study. And if we kind of back up now with that value function, that optimal value function, and look at class 2, then we can either choose to sleep with a value of 0, or we can study and get a nice juicy value of 10. But we get -2 along the way, so the value is actually 8. And back up now to class 1, we could again would lose 2 rewards, so the optimal value is 6. And lastly, the TV state, we can either choose to lose reward by continuing watching TV, or we can quit at no loss of reward and return to 6. So there's no loss of reward here, so the optimal value is 6. Okay, so we can kind of just see that intuitively. But we also have like the optimal action value function, Q star, and this similarly tells us which actions we must take to always win. So in other words, it weights the edges, and we can just follow the edge with the highest value to always win. So if we know this, we're done. For example, at class 1 here, we can see that the action to relax has an optimal action value function of 5, and the action to study has an optimal value function of 6. So we study. We always just choose the max. And if we're in class 2, then we can see that the action to sleep has a Q star value of 0, and the action to study has a Q star value of 8. So we always take the max, so we always study again here. And if we're in class 3, we can see the action to study is 10, and the action to go back to the pub is 9.4. So the max of 10 and 9.4 is 10. So we would study here. So it's reassuring to see that the optimal strategy is to indeed study. Yes, it's better than going to the pub. So we'll see how to actually compute these optimal value functions. But the optimal policy is therefore shown here in the red edges. Okay, and it intuitively relates to the optimal action value function. The optimal policy is always the one that picks the highest Q. Okay, so we can see that the optimal policy, and that's for gamma, is equal to 1. So how do we actually compute that central quality Q star? Well, we do what's called the Bellman optimality equations, and we work our way backwards from the final state. So just looking at the definition here, they're similarly recursively related by the Bellman optimality equations. So this idea that the optimal value function is the max Q star, whereas Q star is also relates to the Bellman expectation equations, which we saw earlier. Okay. So there's this kind of recursive definition again. So just to make this concrete, we'll have a sort of last example of how we can compute the optimal value function and the optimal action value function. So V star and Q star. So for class 3 here, if we record a definition of V star from the previous slide, it's equal to the maximum action value function. And then we can just take that definition out. So it's the maximum of the reward for being in that action plus the discounted summing of the next states. So in this case, it's the maximum of 10 plus 1 time. So we've got it's discounted by 1 times the 0 value. And then we've got to sort of look at it going forward for going down here, where we've got, again, it's discounted by 1, plus there's this 0.2 probability of getting 6, plus 0.4 probability of getting 8, and then plus 0.4 probability of coming back here. And if you sort of assemble that all together, you've now just got the maximum of this Q star being 10, and this Q star, which that all gives you 9.4, which gives us your final 10. So that's how you would actually compute it, again with this kind of one-step look-ahead idea, which is very similar to the example we saw previously. So that kind of concludes this lecture. I appreciate there's been quite a lot of maths and formal notation, which does take a bit of time to sink in, but hopefully you can work your way through some of these examples and maybe have a go running some of that collab, and you'll get more confident in these concepts as you go through the following lectures, as we'll sort of revisit them with more practical applications and more algorithms, which will hopefully make this kind of knowledge come together. Okay, well that concludes this. That's it.